Okay, first, most of the time, okay, the algorithm we taught it before, they fell into a category called supervised learning. Basically, the definition of supervised learning is we would like to solve a problem. This problem would like to find or to mine the relationship between your feature. Okay, we have a model. Okay, so that is your model. All right, and we have a lot of features. And here's our target. We'd like to understand the relation between a lot of features, okay, different dimensions of the features, and the target value. If the target value is a numeric value, and we say it is regression problem. If it is a categorical, for example, 1 or 0, yes or no, several different classes, okay, then it is a classification. We have covered several different algorithms. Regression, we have two different algorithms, linear regression and logistic regression, right? Although we use the word regression, however, logistic regression only deal with 1 or 0 target, all right? However, linear regression can deal with numeric. So basically, logistic regression fell into the category of classification problem, classification algorithms, not a regression. Okay, and usually we draw it like this, right? We have a lot of different features. We have y. So basically, linear regression. Okay, we have a very visualized graph, something like this. Okay, we have to find this line, and this line sometimes you can present it as this way or this way if you have a lot of features. Okay, so the w and x and b are vectors. For logistic regression, okay, it's the same. Usually we write it by using z. Okay, z is a linear combination, okay, of x, something like. But basically y is, and usually it looks like a z shape, a reversed z shape. Okay, for both these kind of algorithm, the philosophy of such kind of algorithm is I would like to find a fitting function, which means I can describe the relationship between x to y. So when you draw x and y on the surface on a multi-dimension space, okay, I would like to find a line, which like linear regression. I would like to find a shape, a curve, like linear logistic regression. I would like to fit this line to the training data set. Okay, as we mentioned before, we have training data set, right? So I'd like to find a line to fit the training data. No matter if it is a line, it is a curve, it is a surface, it is a subspace, whatever. If I can find a simple line or curve to describe the original data, to fit the original data, to fit the training data, then we're done. Okay, that's good. That is good enough for such kind of. That's the first philosophy. For the second one, the other philosophy we call partition. Like what? Like SVM. We have a lot of different features. Okay, you have to notice that I write x1 and x2. There could be multi-dimension space. Okay, so there are two sets of data. Okay, one is right here, the other is right here. The blue ones is labeled as y, for example -1, and the red points right here, they are labeled as y as +1. So for this second type of algorithm, they are trying to partition the original space. The original space can be used to represent the training data, right? Because we have a lot of training data right here. Try to find a way, for example, this line, okay, that is the SVM line, to partition the original data. So basically, it is also a classification problem falls into this category. Okay, to find this line, of course, there are several different ways to find this best line. For example, SVM to find the widest line which can partition these two sets of data. So this is called partition. Okay, of course there are several different ways that SVM can partition this data. These two data sets, as we mentioned before. Okay, you can use linear, which means use a line to partition the data. Okay, or you can do RBM. Okay, there are several different kernels, which I will show you later. There are several kernels. We are in the space, okay? We are in the dimension which is x1 to xn. Usually we write it in this way. It is a dimension with n dimension. R means real number because those are numbers. We have n numbers which can present a space. However, we can do a mapping, space mapping, 就是空间转换 or space transform. We can map this space to, for example, another space which has one more dimension. It is quite simple in the vector space because you can just simply write a function to make the original space which has n dimension to another space which has n plus 1 dimension. If it is more easier for you to partition the original data in n plus 1 dimension and then do it. Okay, there are several different mapping functions can help you to map your data from your n dimension to n plus 1 dimension and even n plus 2 and so on and so forth. And those mathematicians already help us to find those very useful functions to help us to do such kind of mapping, space transform. Okay, so in n plus 1 space, maybe in that space, okay, it is more easily for you to find a surface to partition the original data. So that is another concept to do this model. Unlike fitting function, okay, unlike the green ones, unlike the fitting functions. Fitting function describe the relationship between x and y. However, in SVM, this model describes this line or this surface, and this surface can make a nice partition. And the third, usually, okay, as we mentioned before, it is tree-based. Although it is called tree-based, however, from my opinion, it is still belongs to partition-based algorithm. Why do I say so? Okay, let's take a look at the tree-based. For example, we have a lot of data, okay, at the root. Okay. For example, we have 10 data points, and of course there's for these data points, okay, so you can write it in this way. However, we like to do prediction or to do regression or to do classification of y, and at the root, maybe we can take a look at the y, okay, because y is more important, okay, and we can see that in this data set we have only 10 points, right? I would like to ask a question right here. The question is related to feature, and maybe there is a parameter which is along with this question, and the answer should be yes or no. Based on this question, I can partition the original data, which has 10 data points, to, it is just an example, okay, maybe 3. But the most important things right here is what feature should I ask at this moment, and what is the parameter I should use at this moment, and why I would like to do such kind of partition. So basically, we have several ways, okay, I use another card, okay, we have several ways to evaluate such kind of partition. The first is entropy. We have 3 values right here, right? I give it a name, so that is y root, okay, that's y that, right, it's y right. Add 3 y's right here. What kind of partition in your mind, which is the best partition rules? For my opinion, if I can find a question which is, for example, x1 less than 5.5, okay, this kind of question can partition the original data, 10 data points, to 2 data sets, and y left and y right. All of the y's in y left are the same, and all of the y in the y right are the same. If all the y left in here, in the left node, are all ones, which means, that is a very great question, for example, x1. And at the right hand side, if all the 7 data points at the right hand side are all zeros, if I ask a very, very good question right here, and that would be perfect. And of course, in practice, maybe there has no such kind of perfect features and perfect parameters that can partition the original data into 2 data sets like this. So I can ask a lot of questions, and here are some equations to help you to evaluate which question is the best question. So the first tools we told last week is entropy. In Mandarin, it is 熵嘛，或是底，那中文翻译成乱度也可以。So how do we evaluate? The entropy before you partition is y root. The entropy after you do such kind of partition is y left and y right. You have to make sure the y, the entropy of y, 就是 y 的乱度变得比较整齐一点了。这就是你所想要的。If you can find the x and answer the question and partition the data into 2 data sets, and the entropy of y left and y right decreased, which means most of the data in one data set, the y value are all ones or all zeros, then this question is very valuable. You should ask this question at the first place. So that is entropy. Of course, there are several different evaluation mathematical tools to help you to evaluate. The second one is like Gini, 就是 Gini factor， 就是基尼系数啊。基尼系数就是指的是不纯度嘛。所以你原本的 y root 有多不纯，你拆开之后一个 y left 一个 y right 嘛，对不对？里面有很多拆开的资料点嘛，那变得有多不纯？那我们当然希望纯度越高越好嘛，所以这个问题就问得越好，因为它可以把 y 拆开之后变得越纯越好。因为再讲一遍哈 ，the Gini factor this kind of evaluation they would like to evaluate how pure or how impure the y is. If the question is very, very nice, and the y left and the y right, the component inside the y left and y right should be very pure. For example, all zeros or all ones. And that would be a very nice question. And you should use this as your first question. Okay? There are several different index. 它们有不同的指标, but all of them have the same target, which means they would like to partition the data. And the y, no matter its entropy will decrease, its impurity, 就是不纯度 will decrease, or the chi-square or the variance will decrease, which means the data become more and more all zeros or all ones, and so on and so forth. So you can ask the second question, the third, the fourth, the fifth, until all the y in each node will only contain 1 or only contain 0, and so on and so forth. So you can do a very nice tree-based algorithm to partition the entire data. Although it is, we call it tree-based algorithm, but from my opinion, they are still partition-based algorithm because we can write it in this way. For example, that's x1. For example, we have only 2 features, and we have some data right here, the red ones, And for tree-based questions, okay, maybe the very first question you should ask is to partition this y+1 and y-1 as clean as possible. So sometimes the first question should be look like this. That is the first question. If x2 larger than some value, so the left hand side is larger, okay? So the right hand side, they are all reds. This data point is right here. And left hand side is right here. And then I can ask the second question. Maybe that is right here. And larger than. So at this data point, I have two partition data. Right hand side is the blue one, which is right here. And left hand side is the red data right here. So basically, tree is also if you draw the relation of this tree by using the questions, and you can still observe that okay, that is a space. That's is a space, and we partition the space by using a lot of different questions, by using different features, and each subspace maps to a live node of this tree. As we can see, we try to make each node, each live node, as clean as possible, so that we can do this kind of thing. So from my opinion, tree-based algorithms is still like partition-based algorithms, okay? We just partition the original space into different subspaces, okay? So that is it. Here I'd like to show you some other things by using orange. How do we use orange to deal with all those different algorithms, okay? First, of course, you have to drag one of the data you would like to analyze. So to double click it and select the built-in data set. Let's select one of the data set which is fit for classification. Okay, maybe we use this one, iris. And if you would like to take a look at this data, okay, you drag the data table, okay, and connect it from data to data, and you can see that is the data. What to do is to click the evaluate, drag this one, test and score, and you connect your data to test and score. You have to drag different models from here. In orange, if those algorithms, okay, fell into this category called model, that means they are supervised learning, which I wrote right there. We will talk about unsupervised learning in the next hour. So take a look at this one. It's model. Supervised learning, we have learned what linear regression like this one, right? We have learned logistic regression like this one. We have learned SVM, this one, and we have told you something about tree right here. For algorithms, you can use them to evaluate this data. However, as I said, iris data, okay, they are classification data. This is a classification problem, right? So the Y, the target, is all categories. There are 3 different categories right here. So basically, you cannot use linear regression. Linear regression only deal with numeric target, right? However, logistic regression, SVM, and tree can be used for classification problems. So we connect these 3 algorithms to the analyze process. And at the right hand side for evaluation, okay, and you select confusion matrix right here. So we connect it to here. The evaluation result will be passed to the confusion matrix. And first we double click this. And as we mentioned before, okay, we have several ways to evaluate the training data. Since we only input training data right here, right? So we don't have test data, okay? So we ask the algorithm to help us to do cross-validation. As we mentioned before, you divided the original 150 data points into 10 data sets, and you use 9 parts. You use 9 of them to do training, to train the data, to find the optimized parameters, and you use the only one part to do the evaluation, which is 15 points. All of the data will be tested. We have discussed this last week. So we do this using 10-fold, or you can use 5-fold. So we 3-fold or 2-fold. 2-fold is quite simply we only divide the data into 2 parts, one for training and the other for testing. And we do it again. Use the rest of the data to do training and use the other part for testing. If you have 2 data sets, one for training or one for testing, you can use the other function right here. Okay. So basically, we simply just view the CA, which is classification accuracy, and we can see that all of these 3 algorithms has very high accuracy, which means 96, 95, 94% of the data can be classified into the correct categories. F1 score, precision, recall. You can go to the Wikipedia and to revisit the definition of these 3 different metrics. 好，这个我们上礼拜都上过了哈。And usually, okay, we use F1 to evaluate the capability of these 3 different algorithms. So you can see that for the logistic regression, we have 3 different classes. The actual class is right here. So 50 data point will be classified to the correct iris class code setosa, and only 47 will be classified to the correct versicolor, and 2 right here. Okay, the actual class is Virginica, and this algorithm, logistic regression, misclassify those 2 data points to versicolor, and so on and so forth like this. How about this tree? This one, visualize. Okay, here's the visualize, and here's the tree viewer. So you drag it right here. If you would like to view this tree, you have to do one more thing like this. Because at the right hand side right here, remove this. Okay. Basically, if you would like to draw your tree, basically you need data, you need an algorithm, and you need to draw a tree. There's nothing to do with the test, so you have to draw the tree like this. Okay, you have to connect the data to the tree and the tree to view, and you double click this one again, and you can see there's a pop-up window. Here's our root. And at the bottom right here, that is one of your features, which is called petal length. And here is the equation. If some data, okay, the petal length is less than 1.9, and all the data comes here. Okay, how many data is right here? 50s. And among also those 50 data points, okay, 100% means all of them belongs to one category, iris setosa. So left hand side, the left tree is done. Because I asked a very nice question, which can partition the original data into 2 data sets, and one of the data set is the entropy is quite low, or the purity, or the 纯净度 is quite high, or the variance is quite low, something like that. So that is a very nice question. And at the right hand side, okay, only 50% of the data right here, okay, I have 100 data, okay, and 50% one class and 50% the other class. So I have to ask another question. So the second question is the petal width, less than 1.7 or larger than 1.7. And right here, perfect. At the right hand side, okay, I have 60 46 data points, and 45 of them are all Virginica. So this question is quite nice because the entropy is quite low, the variance is quite low. And so on and so forth. I can ask the third question, which is the petal band is less than 4.9 or larger than 4.9, and so on and so forth, so on and so forth. So you can partition the original 150 data points by using this tree. Okay. Of course, you can control how many questions can be asked. So come back to here. Double click the tree. Okay. There are some interesting settings. Okay. First one, binary tree. Binary tree means you can ask one question and the answer should be yes or no. So the branch is binary. 就是你只能问是非题啦，所以你就岔开嘛，而一次就分两个答案嘛，OK。Second, minimum number of instance in live， 就是说在那个 live node 上啊，最少就是两个点，你不能够把两个点再拆开成两个子点，然后两个子点里面各有一个点。好，因为我们会觉得说，你这样无限拆分下去，看起来有点没效率嘛，所以他说最少要两个点。The second checkbox means you cannot partition a node with only 2 points and further partition it into 2 nodes and each one have 1 node. You can do that. You cannot do that. Okay. The minimum instance, the minimum data point in the live node is 2. Of course, you can change it. Okay. The second one, do not split subtrees smaller than 5. That means at some node you don't do partition if it has less than 5 data points. Okay. So that's one. The limit of maximum tree depth to 100. It means you can only ask at most 100 questions. So you can only have at most 100 levels. Okay, let's take a look at this one. It's called ROC Curve. Confusion metric is one of the very straightforward method that can help you to evaluate how good your model is. But sometimes we use the ROC curve, so you can simply connect it to your ROC curve. Okay, so double click it. So basically, we have 3 models right here, right? 3 models right here. You can simply just click one of them. My current target is one of the Y versicolor, okay? And I select one of the classifier, which is logistic regression, and it shows a curve right here. And right side this is FP rate or 1 minus specificity. What does that mean? FP means false positive. False positive means something you misclassify them. FP 就是 false positive， 后来就是你做错了嘛，其中一种做错 ，OK。At the left-hand side is TP rate, which means true positive. True positive 就是你做对的嘛，他说是 E 就说是 E 嘛，对不对 ？X value is almost 0, right? Almost 0. That means you don't have any false positive， 就是没有做错任何东西，对吧 ？False positive 做错 ，OK。So your false positive rate is 0, okay? At that moment, okay, you take a look at the y-axis. Your true positive rate is not 1.0, it's not 100%, which means if you want to have a classifier which has no false positive， 就是如果你想有个 classifier， 但是它不会做错任何事情的时候，它在判断正确的那一边的时候呢，会有一些瑕疵，它没有办法到100%，可以吗 ？If you want to have a classifier which has 0 false positive, but at the same time, the model you use to evaluate your true positive rate it does not reach to 100%. When you do logistic regression on the target, which is ROC Curve， 好，就是我们现在评估的是 logistic regression 这个 average 嘛，那我们现在评估的是那个 ROC Curve 这个特别的 class 嘛，好，那我们在评估这件事情的时候啊，在不做错的情况之下，其实它没有办法把所有东西都做对，因为它本来就是一个 trade-off。你可以做牺牲嘛？你可以往右走一点啊，你可以往右走一点，比如说你找这个点。Let's take a look at another point, okay? Look at my mouse. In the same scenario, okay? If you want to have 100% true positive, which is right here, so the y-axis is close to 1.0， 就是它左边对过来是1嘛。And then at that moment, okay, your false positive will be something like 0.09 or something。就是说，如果你要 false positive， 就是全部就是做对的时候，就是对的地方要全对的时候，你很有可能这边会做错。我们知道那个 control metric 有4个格子嘛，这4个格子是一个妥协，就是 model 妥协之后的结果嘛，对不对？如果你想要让某一个格子数字提高的话，那另外的格子可能就会被影响到，没有办法做到全部100%的，好吗？这件事情比较直观的看法怎么看呢？就是看 Partitionbased 在这里。好，我们刚刚不是选 logistic regression 吗？对不对？然后我们不是选的这个 ROC Curve 吗 ？OK， 这 ROC Curve 其实原本在它在里面就做错了嘛，对不对？做错了。好，那大家还记得 logistic regression 怎么做吗？一个 z 的曲线嘛，对不对？那这个曲线不是很多那个我们不是有算 A 星跟 B 星吗？那 Orange 告诉我们的答案应该已经是最好的星了，就是他认为 optimize 的结果。可是 optimize 的结果在 ROC Curve 还是做错2个，对，这里做错2个，或者你看的话就这边做错3个。那怎么办？如果你想要提升这个紫色的这一格的时候怎么办？你想提升紫色这一格的时候啊 ，ROC Curve 的那个曲线就会变，比如说。我们之前不是判断赢跟输嘛，对不对？如果你想要让每一次你判断赢都会是对的，那你那个曲线是不是要比较往上推一点，靠向赢那一边？可能往上推一点，靠向赢那一边，你下面就会被拉到，对不对？你下面被拉到的话，你判断输的那个就会被影响。Usually, when we see the ROC curve, how do we define a best trade-off? 因为这是个 trade-off 嘛，你不可能都做对嘛。How do we define such kind of trade-off? Usually, okay, we use a line from that top part, and we approach this curve. And the first time we touch this curve, and this curve, this point will be viewed as the best strategy. Can have the highest false positive and still retain the lowest false positive. Sorry， 就是我们从左上角找一个斜线往下切嘛。你第一个碰到人的话，一定是最左上角的人嘛。那最左上角的人有什么特色呢？就是他在低误判率的情况之下维持高准确率，维持高准确率的情况之下有比较低的误判率啊，所以你越往右下其实就越不好。所以我们光看这个表就可以直接评断 logistic regression 在 ROC Curve 这个 class 里面，它的效力是比较好的，优于其他2个人。但是这个差距很少，大部分我们看到的 ROC Curve 会很怪，就是比较偏下面。我们就找最左上角的就是